Light is both a wave and a particle, and time itself is not what it seems. These are not fictional ideas, but genuine paradoxes shaking the foundations of physics. We are exploring 40 explanations for the universe's most puzzling paradoxes, a journey that will completely reshape your understanding of reality. You will gain a clear and startling picture of how the cosmos truly operates, from the quantum realm to the edge of black holes. How can a cat be simultaneously alive and dead? And why does the universe appear fine-tuned for our existence? These questions have tormented brilliant minds for generations, and their proposed solutions reveal a world far stranger than fiction. By the end, you will see the universe not as a collection of separate objects, but as a deeply interconnected and often baffling whole. What does it truly mean for something to be real? The logic of cause and effect seems to unravel completely with a single act of time travel. You step into the past and prevent your own grandparents from ever meeting. If that succeeds, you could never have been born to make the journey. So how could the event ever happen? This is the grandfather paradox, a thought experiment that exposes a devastating flaw in the idea of visiting yesterday. It suggests the universe would simply not permit such a contradictory loop to form. One compelling solution is that the timeline is self-healing. Any action you take in the past was always a part of that past. Perhaps your attempt to interfere is what accidentally causes your grandparents to meet in the first place. Your presence is not a disruption, but the very trigger that ensures the event you remember unfolds exactly as it always did. In this view, the past is a single, unchangeable record. You cannot create a paradox because you are merely playing a role you always played. Another, even more mind-bending proposal is that you do succeed in changing things. But the moment you alter a key event, the timeline fractures. Instead of erasing yourself, you simply branch off into a new, parallel universe where you were never born. The original timeline, with your own history, continues untouched. You have not rewritten the past, you have just left it behind. This paradox forces a profound question. Is our history a fixed story or a fluid narrative with infinite drafts? The answer might lie not in the large-scale flow of time, but in the bizarre rules of the quantum world, where reality is far less certain than it appears. This unsettling idea of a cat both alive and dead forces us to confront a core quantum strangeness known as superposition. Erwin Schrödinger designed this grim thought experiment not because he believed in undead cats, but to highlight how absurd the math of quantum physics seems when scaled up to our everyday world. Inside the sealed box, a radioactive atom holds the key. The rules of the quantum realm state that this atom exists in a blurred state of both decay and not decay, a combination of possibilities until it is observed. This triggers a chain reaction. A Geiger counter would detect the decay, shattering a vial of poison. So if the atom is in both states, then the cat, tragically, must be in both states as well. It is a living animal and a corpse at the same time. The moment you open the box to look, this superposition collapses. You will find one definite reality, a purring cat or a still one. But what exactly constitutes an observation? Does it require a conscious human mind to peer inside, or is the Geiger counter itself enough to force a decision? This is the heart of the measurement problem, a paradox that asks what truly defines reality. One major school of thought, the Copenhagen interpretation, argues that the act of measurement itself is what solidifies one possibility into our concrete world. There is no single reality until it is observed. In contrast, the many worlds theory offers a breathtaking alternative. It suggests that the superposition never actually collapses. Instead, the moment of decision causes the universe to split. In one branch, you open the box and find a relieved cat. In another parallel branch, an equally real version of you discovers a tragedy. Both outcomes happen just in separate, uncontactable realities. This paradox shatters the classical notion of a single, objective world existing independently of us. It implies that reality at its most fundamental level is a spectrum of potential, waiting for something or someone to bring it into focus. But if the quantum world is this malleable, what happens when we apply its rules to the nature of light itself, a phenomenon that behaves as both a wave and a particle? While Schrödinger's cat questions the nature of reality itself, another paradox stretches time into a malleable fabric. Picture two identical twins. One boards a revolutionary spacecraft and journeys to a distant star at a speed approaching light itself. The other remains firmly on Earth, living a normal life. Upon the traveler's return, a shocking difference is revealed. The astronaut twin is significantly younger than their sibling who stayed behind. This is not science fiction, but a direct consequence of Einstein's theory of relativity. Time itself dilates or stretches out for anything moving at tremendous speeds. For the traveling twin, clocks tick more slowly, biological processes slow down, and they genuinely age less. The paradox emerges when we shift perspectives. From the astronaut's viewpoint, couldn't you argue that the Earth was the one that sped away and then returned? If motion is relative, then the Earth twin should be the younger one. This is the core of the confusion. The resolution lies in a critical asymmetry. The twin on the spaceship is not just moving at a constant velocity. To turn around and come home, they must experience acceleration, a palpable force pushing them back into their seat. They feel the change in motion. The Earth twin, however, feels no such forces. This experience of acceleration breaks the perfect symmetry between the two perspectives. The traveling twins' path through the combined fabric of space and time is fundamentally different, and it is their clock that ultimately logs less time. This bizarre prediction is not just theoretical. We confirm it every day with extreme precision. Atomic clocks carried on airplanes, and especially those on satellites like the ones enabling your GPS, must have their time constantly corrected for this relativistic effect. If engineers ignored this time warp, your phone's map would be off by miles within minutes. This paradox demonstrates that time is not a universal metronome ticking at the same rate for everyone. It is a personal experience woven together with space and deeply affected by how you move through the cosmos. But if the nature of time is so fluid, what can we say about the void from which everything supposedly came? The sheer scale of the cosmos makes the silence profoundly deafening. With billions of stars in our galaxy alone, and many of those likely hosting habitable worlds, the numbers suggest a universe teeming with life. So when physicist Enrico Fermi famously asked, "Where is everybody?" he was pointing to a gaping contradiction between high probability and zero evidence. This is the Fermi Paradox, and its possible solutions are as haunting as they are fascinating. One chilling possibility is that intelligent life carries the seeds of its own destruction. Perhaps every advanced civilization, upon reaching a certain technological level, inevitably discovers the means for its own annihilation through war, environmental collapse, or uncontrollable artificial intelligence. In this grim scenario, the great filter lies not in the origin of life, but in its survival. The silence of the universe would then be a cemetery quiet, a warning from an empty cosmos. Another theory is far less dire but just as isolating, the zoo hypothesis. Imagine we are living in a kind of cosmic wildlife preserve. Advanced alien societies know we are here, but they have chosen a strict policy of non-interference, observing us from a distance to allow our culture to develop naturally, or perhaps to avoid contaminating a primitive society. We are the exhibit in a galactic museum, unaware of the curators. Then there are the practical limitations. The distances between stars are almost unimaginably vast. Even if a civilization wanted to visit, the energy and time required might be insurmountable. Or maybe we are simply not listening correctly. We search for radio signals, but a truly advanced culture might use a technology for communication that is as invisible to us as radio waves would be to an ancient human. This paradox forces a deep reflection on our own future. Are we an incredibly rare fluke, a lonely beacon in the dark? Or are we a young species on the cusp of discovering we are part of a crowded yet silent community? The answer may determine whether humanity is destined for a solitary existence or a shared cosmic destiny. This contemplation of cosmic laws and life leads us directly to a paradox that challenges the most fundamental rule of physics itself. A tiny, intelligent demon could seemingly outsmart one of physics' most unbreakable laws. James Clerk Maxwell proposed this brilliant thought experiment to challenge the second law of thermodynamics, the principle that disorder or entropy always increases. Picture a microscopic being stationed at a tiny door between two chambers filled with gas. This demon watches molecules approach. When it sees a fast-moving molecule coming from the left chamber, it opens the door to let it pass to the right. When a slow molecule approaches from the right, it lets that one through to the left. Over time, the left chamber grows cold, filled with sluggish molecules, while the right chamber becomes hot, packed with energetic ones. The system becomes more ordered, not less. Entropy has decreased, all without the demon apparently doing any work. This appears to be a perfect perpetual motion machine, violating a foundational rule of the universe. For over a century, this paradox haunted physicists. How could a simple act of selection break a law thought to be absolute? The resolution arrived not from discarding thermodynamics, but from expanding it to include a new concept, information. The demon is not working for free. To sort the molecules, it must first gather information about their speeds. It needs to measure them to see which are fast and which are slow. This act of measurement, of acquiring information, requires energy. Even if that energy is minuscule, it exists. More crucially, the demon's mind, or its memory, would eventually fill up with data about all the molecules it has observed. To continue its work, it must erase this old information to make space for new measurements. And here lies the final, brilliant piece of the puzzle. The act of erasing information is not a free process. It physically generates heat. This heat dissipates into the environment, increasing the overall entropy of the entire system, demon and all. The cost of obtaining and forgetting information always outweighs any local order the demon creates. The second law stands triumphant. This revelation forged a deep, unexpected link between the abstract world of information and the concrete physics of energy and heat. It shows that information is not just an idea, it is a physical thing with real, energetic consequences. A thought experiment about a hypothetical demon ultimately proved that knowledge itself has a tangible weight in the cosmos. This profound connection between information and reality becomes even more bizarre when we examine how particles can be linked across the vast emptiness of space. Two particles born from the same quantum event fly apart across the galaxy. You measure one and find its spin points up. Instantly, you know its distant partner must be spinning down. This instantaneous connection defies everything we know about space and communication. Albert Einstein was deeply troubled by this, calling it spooky action at a distance. He, along with physicists Podolsky and Rosen, crafted the EPR paradox to argue that quantum mechanics must be incomplete. They believed in locality, the sensible idea that objects can only be influenced by their immediate surroundings, not by events happening light years away with no time for a signal to travel between them. How could one particle know what was happening to the other faster than light without some hidden, undiscovered variable orchestrating the outcome? For decades, this was a philosophical debate about the nature of reality. Then, physicist John Bell found a way to test it. He developed a mathematical theorem, now called Bell's inequality, which provided a clear experiment to distinguish between local hidden variables and true quantum weirdness. When scientists finally performed these experiments, the results were unequivocal. The universe voted for spookiness. Entanglement is real, a fundamental feature of our world, not a flaw in the theory. This means the universe is fundamentally non-local. Particles that have interacted remain part of a single, unified system, regardless of the distance between them. This profound interconnectedness is not just a curiosity. It is the engine of emerging technologies like quantum computing, where entangled qubits can perform calculations impossible for ordinary computers, and quantum cryptography, where any attempt to eavesdrop on a message instantly disrupts the fragile entangled state, alerting the users. We live in a cosmos where separation may be an illusion, and everything is subtly, instantly linked. This deep, non-local connection forces us to confront another fundamental puzzle, one that deals with the very concept of endlessness and the size of the universe. An infinite hotel never posts a no-vacancy sign. The great mathematician David Hilbert conceived of a grand establishment with an endless number of rooms, each one already occupied by a guest. Now a new traveler arrives desperate for a place to stay. Common sense suggests they are out of luck, but in the realm of infinity, common sense fails. The manager simply asks every current guest to move one room over. The guest in room 1 moves to room 2, the guest in room 2 moves to room 3, and so on, all the way down the infinite corridor. This simple shuffle leaves room 1 completely empty and ready for the new arrival. The hotel remains fully occupied, yet it has just accepted another person. The strangeness only deepens. What if an infinitely long bus pulls up carrying an infinite number of new guests? No problem. The manager moves the current guest in room 1 to room 2, the guest in room 2 to room 4, the guest in room 3 to room 6, effectively moving everyone to even-numbered rooms. This brilliant maneuver instantly frees up every single odd-numbered room, an infinite collection, for the infinite number of new passengers. This is the mind-bending reality of Hilbert's hotel, a thought experiment that reveals how infinity operates by its own bizarre logic. It demonstrates a property that seems impossible to our finite minds. An infinite set can have a part that is just as large as the whole. The number of rooms is the same as the number of even-numbered rooms, which is also the same as the number of rooms numbered greater than 1,000. They are all infinite in a way that allows them to be perfectly matched one-to-one. This paradox is not just a mathematical curiosity, it has profound echoes in our understanding of the cosmos. If our universe is truly infinite, then somewhere in the vastness, every possible arrangement of atoms must repeat. There is another Earth, another you, and an infinite number of variations, all contained within the same unending reality. Hilbert's hotel forces us to abandon our intuition and think logically about the endless, revealing that infinity is not a number but a process, a concept that continually escapes our grasp. This struggle with the infinite leads us directly to a paradox that touches the very essence of change and the flow of time. A loop in time can create something from nothing. The Bootstrap Paradox imagines a world where an object or a piece of information has no true beginning. Think of a time traveler who carries a copy of Shakespeare's complete works back to the Elizabethan era. She hands the book to a young, aspiring William Shakespeare, who then simply transcribes the plays and passes them off as his own genius. The plays are published, become legendary, and survive for centuries until that very same copy is found and taken back in time. So, who actually wrote Hamlet? The plays were never created by anyone, they just always existed, trapped in an endless, originless cycle. This paradox violently severs our most basic understanding of cause and effect. An event is supposed to have a cause that comes before it, but here the effect is its own cause. The plays cause their own existence. This is not just a fanciful story, it emerges from serious physics. Within the framework of general relativity, certain extreme geometries of spacetime, known as closed time-like curves, could theoretically allow for such loops. An object traveling along this path would literally meet its own past. The Bootstrap Paradox forces us to question the very nature of creativity and originality. If such loops are possible, then every great invention, every symphony, every fundamental equation could, in theory, be a gift from the future, with no original author. It paints a picture of a universe where history is not a straight line, but a tangled knot, where things simply are because they always were. This strange looping of cause and effect becomes even more extreme when we try to merge the rules of the very small with the laws governing the very large. A black hole presents physics with its most devastating dilemma. When any object, a book, a star, or even a person, crosses the event horizon, it is lost to our universe forever. According to Einstein's general relativity, the black hole only remembers three simple things about the devoured matter: its total mass, its electric charge, and its spin. Every other detail, the specific atoms that made up the book, the memories of the person, the intricate information that defined those things, is utterly erased, crushed into a single point of infinite density at the singularity. Yet quantum mechanics, the rulebook for the subatomic world, holds one principle as absolutely sacred: information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, always be recoverable. This is the black hole information paradox, a direct war between our two most successful theories of reality. Stephen Hawking's own work intensified this conflict. He discovered that black holes are not completely black. They slowly leak a faint glow of radiation, now named Hawking radiation. This process causes the black hole to gradually evaporate, shrinking over eons until it potentially vanishes entirely. And here lies the crisis. If the black hole disappears, what happened to all the information about the things that fell in? Was it truly annihilated, violating quantum law, or is it somehow preserved? One compelling solution suggests the information is not lost inside, but carefully encoded in the Hawking radiation itself. This radiation would not be random noise, but a complex signal imprinted with the history of everything the black hole consumed. Escaping this information from the grip of the event horizon seems impossible, yet quantum effects like entanglement might provide a backdoor, allowing data to leak out in a highly scrambled form. Another, even more profound idea is the holographic principle. It proposes that all the information describing the three-dimensional volume of a black hole is actually stored on its two-dimensional surface, the event horizon, like a cosmic hologram. The falling matter's information is smeared across this boundary, preserved forever in a pixelated code on the ultimate screen. The three-dimensional reality we associate with the interior is just a projection of this encoded data. This paradox is not a minor puzzle, it is a fundamental battle for the soul of physics. Its resolution will force us to rewrite our understanding of space, time, and information, likely revealing that our universe operates in a way far stranger than a simple void. This struggle to understand the fate of information in the most extreme environments naturally leads us to a paradox about the entire cosmos and the mysterious force causing it to fly apart. The darkness of the night sky holds a secret that contradicts an infinite cosmos. If the universe were truly endless and static, packed with an infinite number of stars, then every single direction you looked in the night would eventually land on a star's surface. The collective glow from this celestial sea of suns should make the entire night sky blaze with the brilliance of daylight. This glaring contradiction is Olbers Paradox, a puzzle that troubled astronomers for centuries. The solution lies not in a lack of stars, but in the dynamic nature of the cosmos itself. First, the universe has a finite age. Light travels at a fixed speed, not instantaneously. This means we can only see the stars whose light has had enough time to reach us since the beginning of everything. We live inside a bubble of visibility called the observable universe, and beyond its edge, the light from countless other stars simply has not arrived yet. The second, and perhaps more profound, factor is the expansion of space. As distant galaxies rush away from us, their light is stretched on its long journey across the cosmos. This stretching shifts the light toward the red end of the spectrum, robbing it of energy and causing it to dim significantly. The more distant the star, the more its light is redshifted into obscurity, or even into invisible infrared. So the darkness above is not an empty void, it is a historical record. It tells us the universe had a definite beginning and has been evolving and stretching ever since. We gaze up at a sky that is dark precisely because the cosmos is not infinite and eternal in the way we once imagined, but is instead a vast, expanding story with a first chapter. This cosmic limit on what we can see mirrors a more intimate limit on what we can choose, leading to a paradox that questions the very nature of our own decisions. Your attempt to change the past could be the very reason it unfolds as you remember. This is the Predestination Paradox, a trap of time where every action you take to alter history only locks it more firmly into place. Think of a person who travels to the past to stop a terrible fire. In their rush to prevent it, they accidentally knock over a lantern, sparking the very blaze they hoped to extinguish. Their future was not changed, it was guaranteed by their own intervention. The effect becomes its own cause, creating a perfect, inescapable loop where free will seems like a cruel illusion. You believe you are making a choice, but you are merely fulfilling a script written by your own future self. This is not just a philosophical puzzle, it emerges from the hard math of general relativity. Certain extreme warps in spacetime, known as closed time-like curves, could theoretically allow for such journeys into one's own past. If these paths exist, then the universe itself might be a vast, intricate machine where every event is predetermined. The past, present, and future would all be equally real and fixed, a single, unchangeable block. This challenges the very core of human experience, the feeling that we are the authors of our own lives. Are our decisions genuine, or are we just actors reading lines from a story that has already been written? The Predestination Paradox suggests that destiny is not a force pulling us forward, but a loop we are forever tracing with our own feet. This profound questioning of cause and effect becomes even more disorienting when we look at how the simple act of looking at something can change its fundamental nature. The very act of looking seems to force the quantum world to make up its mind. A particle can be in many places at once, a blur of potential, until the moment we try to pin it down with a measurement. Then and only then does it snap into a single, definite location. This is the measurement problem, and it asks a deceptively simple question with no easy answer. What, in the end, counts as a measurement? Does it require the conscious awareness of a human scientist peering at a screen, or is the click of a Geiger counter, a purely mechanical event, enough to collapse the wave of possibility into one concrete reality? The boundary is hopelessly fuzzy. If a single atom is in a superposition and it triggers a device, is the device now also in a superposition until a person reads its output? Where does the chain of quantum weirdness end and our stable, classical world begin? The Copenhagen interpretation, long the standard view, draws a firm line. It states that the macroscopic, classical world of measuring devices causes the collapse. The moment a quantum system interacts with a large, classical apparatus, the superposition is destroyed. But this has always felt a bit like a cheat, a way to sidestep the problem by declaring that the rules mysteriously change at a certain size scale. In stark contrast, the many worlds interpretation refuses to acknowledge any collapse at all. It proposes that every possible outcome of a quantum event actually happens. The universe constantly branches, splitting into a multiverse of parallel realities. In one world, you see the particle here. In another, an identical version of you sees it there. There is no single outcome, only an ever-expanding tree of possibilities, each one real. Other theories attempt to find a middle ground. Objective collapse models suggest that superpositions are inherently unstable. They cannot last forever and will spontaneously collapse after a certain time, with gravity perhaps being the trigger that forces reality to choose. This would mean our classical world emerges not from observation, but from a fundamental physical process. The measurement problem remains the deepest wound in the heart of quantum mechanics. It reveals that our most successful theory of the small-scale universe is silent on the very process that connects it to the world we see and touch. We are left wondering if reality is a fragile thing, brought into being by our gaze, or if our own sense of a single, shared experience is the ultimate illusion. This struggle to define something as fundamental as a measurement leads us to an even more basic question, one that philosophers and physicists have wrestled with for millennia. What is the nature of nothingness itself? Even the emptiest space in the universe is not truly empty. According to quantum field theory, the vacuum is a seething, bubbling sea of activity, where virtual particles and their antiparticles spontaneously flicker into existence for the briefest moments before annihilating each other. This quantum foam should be bursting with an absolutely staggering amount of energy, a vacuum energy density so immense that it should warp the fabric of the cosmos beyond recognition. The math predicts a number so large it defies comprehension. Yet when we look out at the universe, we measure the effect of this vacuum energy, often called dark energy, and find a value that is not just small, but shockingly so. The observed energy is about 120 orders of magnitude smaller than the prediction. To grasp that scale, imagine the difference between the size of a single atom and the entire observable universe, and then square that unimaginable difference. This is not a small error, it is a catastrophic failure of our theories, aptly named the Vacuum Catastrophe. It means we are fundamentally misunderstanding something profound, either about the nature of empty space or about gravity itself. How can our most successful theory of the small be so spectacularly wrong about the energy of nothing? One possibility is that there exists a perfect, yet completely unexplained, cancellation mechanism. Perhaps the various contributions from all the different quantum fields somehow add up to almost exactly zero, like a complex equation where immense positive and negative values miraculously balance out. Another, more radical idea from the string theory landscape is the multiverse. In this view, our universe is just one bubble in a vast cosmic foam, each with its own random value for the vacuum energy. Most of these universes would have such a high cosmological constant that galaxies and stars could never form. We, of course, find ourselves in one of the rare, habitable bubbles where the value is almost zero, because that is the only kind of universe where life like us could arise to measure it. This paradox stands as a glaring monument to our ignorance, a clear signal that bridging the gap between quantum mechanics and general relativity will require a revolution in physics. The silence of empty space is screaming at us that we are missing a fundamental piece of the puzzle. This deep disconnect in our understanding of energy and gravity forces us to re-examine other fundamental relationships, including the delicate interplay between cause and effect at relativistic speeds. A message sent faster than light could be received before it was ever transmitted. This is the startling premise of the Tachyonic Antitelephone, a thought experiment built around hypothetical particles called tachyons. Unlike everything else in the universe, tachyons would be born moving faster than light, and according to the strange math, they would actually gain energy as they slowed down, with light speed itself being an unreachable lower limit. Now, imagine using such a particle to send a signal. From your perspective, you send a message to a distant star system, but because the tachyon is moving faster than light, from the viewpoint of someone at the destination, the effect, the arrival of your message, could actually occur before the cause, the moment you decided to send it. They could receive your warning, reply instantly with their own tachyon message, and you could get their reply before you ever sent your original signal. This is a direct violation of causality, shattering the logical sequence of events that holds our experience of reality together. The universe would become a place of pure paradox, where you could prevent your own actions by learning their consequences in advance. So why does physics seem to forbid this? The answer lies in the very architecture of relativity. Einstein's theory carefully weaves space and time into a single fabric where the speed of light is the ultimate cosmic speed limit for any object or information that carries energy or a signal. This limit is not just a barrier, it is the foundation that preserves cause and effect for all observers. If even a single tachyon could be used to transmit one bit of information, that entire causal structure would crumble. Most physicists conclude that tachyons simply cannot exist in our universe, or if they do exist as mathematical curiosities in some theories, they must be fundamentally unable to interact with normal matter in a way that allows for signaling. They cannot be harnessed to build a telephone. This paradox is not a blueprint for a time machine, but a profound demonstration of why such a machine is likely impossible. It reveals that the speed of light is more than just a number. It is the guardian of cosmic order, ensuring that yesterday always comes before today. This careful protection of sequence makes the next paradox all the more baffling, as it asks what happens when two particles lose their individual identities entirely. Our own bodies are living proof that identity is not a fixed state. Every cell in your skin, every strand of hair is replaced over the years, yet you still feel like the same person. This ancient puzzle, known as the ship of Theseus, asks a deceptively simple question. If a legendary vessel has every single one of its wooden planks replaced during a long voyage, is it the same ship that first set sail? And if you gathered all the old, discarded planks and reassembled them into a ship, which one now holds the true identity, the continuously repaired vessel or the reassembled relic? This is not just a philosophical debate for sailors, it strikes at the heart of what we mean by an object's identity over time. Does it lie in the material it is made of, the specific atoms, or in the pattern, the structure, and the history it carries forward? Physics delivers a startling answer when we apply this question to the fundamental building blocks of reality. In the quantum world, the concept of individual identity for particles completely evaporates. According to quantum field theory, what we call an electron is not a tiny, permanent marble. It is a localized excitation, a tiny vibration, in a universal electron field that permeates all of space. Every electron in the universe is an identical ripple in this same underlying field. They are utterly indistinguishable. There is no way to mark one electron and track it as your special particle. If two electrons interact and then fly apart, it is fundamentally meaningless to ask which one is which. They have swapped their identities, or more accurately, they never had unique identities to begin with. This profound indistinguishability is not a minor detail. It is the engine behind the structure of our universe. It leads directly to the Pauli exclusion principle, the rule that prevents all the electrons in an atom from collapsing into the same lowest energy state. This is why matter is stable and occupies space, why you do not simply fall through the floor. The paradox of the ship forces a radical shift in perspective. The identity of an object may not be in its substance, but in the persistent relationships and the information that defines its configuration. A ship is a ship not because of its specific planks, but because of the organized way those planks are held together. An atom is an atom not because it contains specific electrons, but because of the quantum state that defines their arrangement. This idea connects deeply to conservation laws and the symmetries of nature. The total charge in the universe is conserved not because we are tracking individual electrons, but because the underlying laws are symmetric. The pattern persists even as the participants are completely interchangeable. So what truly defines you? Is it the atoms that currently make up your body, almost none of which were there 7 years ago? Or is it the stable, continuous pattern of information that is your mind and memories? The ship of Theseus reveals that persistence through time is not about preserving stuff, but about preserving a coherent story. And this very question of information and identity becomes violently warped when we confront the ultimate cosmic shredder, a black hole. A black hole's event horizon should be a moment of serene transition, a point of no return where an astronaut feels nothing at all. This is the no-drama prediction of general relativity, where space-time curves so steeply that not even light can climb out, yet the falling observer crosses that boundary without a jolt. But quantum mechanics paints a far more violent picture. From the perspective of someone watching from a safe distance, all the information about what falls into the black hole is thought to be stored or encoded on this surface. To reconcile these two views, the theory suggests that the horizon cannot be a placid place after all. Instead, the infalling astronaut would not encounter empty space, but a searing wall of high-energy radiation, a literal firewall that would instantly incinerate anything crossing it. Here lies the devastating Firewall Paradox, a direct clash between the smooth geometry of Einstein's gravity and the informational demands of the quantum world. How can the same point in space be both a featureless curtain and a blazing inferno? The paradox suggests that one of our core principles must be wrong. Perhaps the equivalence principle, which states that free fall feels like floating in empty space, breaks down at the quantum level, or maybe our understanding of how information escapes a black hole is flawed, and the horizon is not the simple boundary we imagined. Resolving this conflict may require a radical new vision of spacetime itself, where the concepts of location and separation dissolve into something more fundamental. Theories like string theory propose that black holes are actually tangled knots of cosmic strings, while loop quantum gravity suggests spacetime is woven from discrete, finite loops, preventing the infinite energies of a firewall. This paradox is more than a theoretical curiosity. It is a screaming signal that our two most successful theories of reality are fundamentally incompatible when pushed to their limits. The serene silence of a black hole's edge masks a battle for the soul of physics, a battle that can only be won by discovering the elusive theory of quantum gravity. This confrontation at the precipice of a black hole forces us to look back to the very beginning of everything, to a moment when the entire universe was infinitely smaller and denser than any singularity. The serene violence of a black hole's firewall paradox forces us to look backward to the very inception of space and time. A theorem forged by physicists Bohr, Guth, and Vilenkin presents a stark conclusion. Any universe that has on average been expanding throughout its history must have a definite beginning in the past. There is no escape, no smooth continuation back into eternity. The cosmic story, according to this rigorous math, has a first sentence, yet this undeniable starting point creates an intellectual chasm. What could possibly have caused the beginning of everything? The very concept of a cause requires something to come before, a prior event in time. But if time itself began with the universe, then the question of what happened before becomes meaningless, a grammatical error in the language of physics. We are left with the profound paradox of something emerging from absolute nothing, not just an empty void, but the absence of space, time, and physical law. How can reality spontaneously ignite from a state where the very rules for ignition do not yet exist? Some cosmological models attempt to sidestep this singular birth. The cyclic universe proposes an endless series of big bangs and big crunches, a cosmic heartbeat where each collapse gives rise to the next expansion. In this view, our universe is just one cycle in an infinite series, having no ultimate beginning. Another elegant idea is the no-boundary proposal, which suggests that if we could rewind time to the very start, the distinction between time and space would blur away. There would be no sharp, singular point of creation, but rather a smooth, rounded-off geometry, like the North Pole of the Earth, where asking what came before is as nonsensical as asking what is north of the North Pole. Then there is the quantum approach, which argues that the universe did indeed arise from nothing, but that nothing is not truly empty. In the framework of quantum gravity, nothing is a seething potential, a realm where fluctuations can spawn entire cosmos. Our universe might simply be one particularly successful bubble in an eternal quantum foam, a random but inevitable event in a meta-reality that transcends our notions of before and after. This paradox forces us to redefine nothingness itself. Is it a complete absence of all things and laws, or is it a fertile ground pregnant with possibility, governed by a deeper, perhaps mathematical, necessity? The quest to understand the ultimate origin reveals that our very idea of causality, the bedrock of science, may be a local phenomenon, a rule that only applies within the universe, not to the universe as a whole. We are left staring at the ultimate question, not of what happened at the beginning, but why there is a beginning at all. This search for a first cause leads us to another profound mystery, one where particles communicate instantly across the cosmos, defying the very speed limit that defines reality. A decision made in the present appears to rewrite a particle's history. This is the quantum eraser paradox, a stunning experiment where the rules of cause and effect seem to run in reverse. The setup is ingenious. A single particle, a photon, is sent toward a screen with two slits. As it passes through, it behaves like a wave, interfering with itself to create a distinct pattern. But if you place a detector to see which specific slit it went through, that act of observation collapses the wave and the interference pattern vanishes. The particle acts like a single, localized object. Now, here is the twist, the delayed choice. What if you wait until long after the particle has passed through the slits and is already on its way to the final screen to decide whether or not to look at the which path information? Astonishingly, the result on the screen seems to change based on that later decision. If you choose to erase the path data, the wave-like interference pattern magically reappears. If you retain it, the pattern remains a bland blob. It looks for all the world as if your choice today reached back in time to tell the particle how to behave yesterday. But this is an illusion, a trick of quantum correlation. No message is actually sent backward. The key is that the which path information and the final detection are quantum entangled. They are two parts of a single, inseparable system. You cannot see the consequences of your choice to erase or not erase until after you have collected both pieces of the puzzle and compared them. From your perspective in the lab, the data appears to show a changing past, but in reality, the entire sequence of events was fixed from the moment the particle was emitted, its fate intertwined with the fate of the measuring device. The past does not change, our knowledge of it does. This paradox forcefully demonstrates that entangled particles do not communicate, they correlate. They are like a pair of gloves, one left-handed and one right-handed, sent to opposite sides of the galaxy. The moment you open your box and find a left-handed glove, you instantly know the other is right-handed. You did not cause it to be right-handed, you simply revealed a property that was established the moment the gloves were paired. The quantum eraser works the same way. Your delayed choice does not influence the particle's history. It merely determines which aspect of its pre-established, entangled nature you get to see, the wave-like aspect or the particle-like aspect. This shatters our classical domino chain view of causality. In the quantum world, cause and effect are not a straight line, but a tangled web of connections that only make sense when viewed as a completed whole. We are forced to accept that the universe at its most fundamental level is not a collection of isolated events, but a deeply interwoven tapestry where time itself may be an emergent property, not the master of the show. This profound challenge to our experience of a linear timeline leads us to a different kind of paradox, one that asks if everything we perceive is merely an elaborate simulation. Our reality could be an elaborate digital construct running on a computer built by a vastly more advanced civilization. This is the simulation hypothesis, a modern paradox that merges philosophy with cutting-edge cosmology. The argument, popularized by philosopher Nick Bostrom, rests on a startling statistical probability. If even one advanced civilization ever develops the ability to create hyper-realistic simulations of conscious beings, and if they have any interest in running such programs, then the number of simulated minds would quickly dwarf the number of original, biological ones. Within this cosmic census, the odds are overwhelming that we are not the first generation, the creators, but one of the countless simulations spawned by their technology. The world you perceive, with all its richness and physical laws, might simply be the output of a complex program. This idea forces a radical reassessment of everything. Do the fundamental constants of physics, like the speed of light or the strength of gravity, reflect immutable laws of nature, or are they merely the programmed parameters of our simulation, lines of code that could, in theory, be altered? The glitches we sometimes attribute to quantum uncertainty could be the equivalent of processing lag or background noise in the system. This paradox challenges the very definition of what is real. If the consciousness we experience is indistinguishable from that of our hypothetical creators, then does it matter if our universe is base reality or a simulation? The emotions you feel, the bonds you form, the beauty of a sunset, all of these are real to you, regardless of the substrate they run on. The simulation argument is not a claim that we are living in a video game, but a profound thought experiment about the nature of existence and the ultimate potential of information processing. It suggests that reality might not be a single layer, but an infinite regress of simulations within simulations, a cosmic matryoshka doll of created worlds. As we push the boundaries of our own virtual reality and artificial intelligence, we are taking the first tentative steps toward becoming the very gods whose existence we question. This contemplation of programmed realities leads directly to a more tangible mystery, one written in the irreversible flow of time and the increasing disorder of our world. The fundamental equations of physics show no preference for the future over the past. If you filmed a single collision between two atoms and played the recording in reverse, you would be unable to tell which version was the real one. The microscopic laws are perfectly time-symmetric, yet our world is saturated with irreversible events. A shattered glass does not reassemble, a log burns to ash but never reforms, and we remember yesterday with clarity while tomorrow remains a mystery. This glaring contradiction is the Loschmidt paradox, and its resolution uncovers the origin of time's arrow. The culprit is not the laws themselves, but the specific starting point of our entire cosmos. The Big Bang was a state of extraordinarily low entropy, a condition of almost unimaginable order. From that singular, highly ordered beginning, the universe could only evolve in one statistically overwhelming direction, toward states of higher disorder and higher probability. This is the statistical heart of the second law of thermodynamics. It is not an absolute prohibition, but a matter of staggering odds. While it is theoretically possible for all the air molecules in a room to spontaneously crowd into one corner, suffocating everyone inside, the probability of this happening is so astronomically small that it effectively never occurs in the lifetime of the universe. We see this play out in the simplest of events. An ice cube melts in your glass of warm water because the dispersed, high-entropy state of liquid water is vastly more probable than the ordered, crystalline structure of the ice surrounded by cooler water. The reverse process, where warm water spontaneously draws heat from its surroundings to form an ice cube, would require a fantastically unlikely coordination of trillions of water molecules. This deep connection between cosmology and a melting ice cube is profound. The reason we remember the past and not the future is that the past is a state of lower entropy. Our memories are physical structures in our brains, and forming them is a process that increases entropy, creating a reliable record of the lower entropy state that preceded it. We are carried along by this immense, universe-wide gradient from order to disorder. Time has a direction not because of the rules of particle physics, but because of a one-time, singular event at the dawn of everything. This statistical understanding of time's arrow forces us to confront how information behaves when the fabric of space-time is warped beyond recognition, in the quest to unite quantum mechanics with gravity. Our tangible three-dimensional world might be a magnificent illusion, a holographic projection from a distant two-dimensional surface. This is the startling claim of the holographic principle, a concept born from the fiery paradoxes of black hole physics. It began with a profound discovery about black holes, that the maximum amount of information a black hole can contain is not proportional to its volume, but to the area of its event horizon. The entire story of everything that falls in is painted onto this spherical boundary, one bit of information per tiny Planck area. The cosmos itself, then, might operate on the same principle. All the information that describes the stars, planets, and even you in your room could be encoded on a vast, remote surface at the edge of the observable universe. How can the rich depth of our reality be perfectly captured on a flat screen? Think of a common hologram on a credit card. The flat, shiny surface contains all the data needed to project a three-dimensional image that changes as you move your head. The holographic principle suggests our universe is a far more sophisticated version of this, with the fundamental pixels of reality being unimaginably small. This directly challenges our classical intuition about space. We feel we live in a genuine volume, but this principle implies that volume, and the gravity within it, emerges from complex quantum interactions happening on a lower dimensional boundary. It is as if the world we experience is the result of a cosmic computation occurring on the surface of a sphere we can never see. This radical idea provides a potential bridge between the warped geometry of general relativity and the frantic quantum activity of the microscopic world. Gravity may not be a fundamental force, but a collective consequence, an emergent phenomenon arising from the entangled information of countless quantum bits on the universe's ultimate screen. Accepting this means accepting that spacetime itself is not a primary stage, but a secondary, approximate reality that congeals from something deeper, a network of information. This profound redefinition of reality forces us to reconsider everything we think we know about cause and effect, leading to a paradox that strikes at the very heart of human experience, the ancient debate between free will and determinism. A vast intelligence could calculate the entire future from a single snapshot of the present. This is the audacious claim of Laplace's demon, a thought experiment from the 19th century. If this demon knew the exact position and momentum of every atom in the cosmos, and understood all the forces acting upon them, then the entire tapestry of future events would be laid bare. Every thought you will have, every choice you will make, would be nothing more than the predetermined outcome of a cosmic chain reaction set in motion at the beginning of time. In this utterly deterministic view, free will is a comforting story we tell ourselves, a beautiful and persistent illusion. The universe would be a colossal clockwork mechanism, ticking forward along a single, unchangeable path. Yet modern physics has introduced cracks in this perfect machine. The quantum world rebels against such rigid predictability. Events like the decay of a radioactive atom are fundamentally probabilistic. There is no hidden clockwork we can uncover to say exactly when it will happen. We can only calculate the odds. This inherent randomness at the heart of matter suggests the future is not a single, pre-written script, but a book of possibilities. Furthermore, chaos theory reveals that even without quantum weirdness, the universe is inherently unpredictable. The flap of a butterfly's wings can influence weather patterns weeks later. In any system of immense complexity, tiny, immeasurable differences in the starting conditions can balloon into wildly divergent outcomes. This sensitive dependence makes long-term prediction practically impossible, even for our all-knowing demon, because it could never measure every variable with infinite precision. So where does this leave our sense of agency? Are we merely complex biological machines playing out a script, or are we genuine authors of our own lives? The resolution may lie in understanding that different levels of reality operate by different rules. The deterministic laws of gravity and motion govern the planets in their orbits, creating a stable stage. On that stage, the probabilistic and chaotic interactions of countless particles give rise to the emergent phenomenon of consciousness, a process so complex and self-referential that it generates genuine choice and creativity. Your decision to watch this video was not predetermined by the state of the universe at the Big Bang, but emerged from the unique, intricate pattern of your memories, desires, and thoughts in this very moment. You are not a spectator in your own life, you are an active participant shaping the narrative. This profound intersection of physics, philosophy, and ethics forces us to ask why the stage itself, the universe with its fundamental constants, seems so perfectly arranged for our existence in the first place. The precise settings of our universe feel almost too perfect to be an accident. The force of gravity, the mass of an electron, the strength of the nuclear forces, all seem balanced on a razor's edge. If gravity were just a tiny bit stronger, every star would burn through its fuel in a cosmic flash, snuffing out any chance for life to evolve. If the electromagnetic force were slightly weaker, atoms could not hold together and chemistry itself would fail. This is the fine-tuning paradox, a puzzle that asks why the fundamental constants are so exquisitely calibrated for our existence. One compelling answer is the anthropic principle. In its simplest form, it states that we observe a universe compatible with life because we are here to observe it. If the constants were any different, no one would be around to wonder about them. It is a cosmic version of a survivor's bias. We see the one winning lottery ticket, not the countless losing ones. But this feels deeply unsatisfying, like explaining a miracle by saying someone had to win. Another, more expansive solution is the multiverse. This theory suggests our universe is just one bubble in an infinite cosmic foam, a vast landscape where each universe is born with its own random set of physical laws and constants. In nearly all of these universes, the numbers are wrong and they remain dark, empty, and sterile. But by pure chance, in a few rare bubbles like ours, the numbers line up perfectly, allowing for galaxies, stars, planets, and life. We are not special, we are just lucky. A third possibility is that these constants are not random at all. Perhaps they are the inevitable outcome of a deeper, more fundamental theory of everything, a set of equations that leaves no room for variation. The numbers are what they are because the math demands it, and life is a fortunate but secondary consequence of this underlying cosmic logic. This paradox forces us to confront the very nature of our reality. Is our universe a product of intentional design, a staggering fluke in an infinite multiverse, or the only possible outcome of a beautiful mathematical truth? The answer may lie beyond our current grasp, a reminder that the cosmos holds mysteries that challenge our deepest intuitions. This search for a deeper logic in nature's laws brings us to a paradox that questions the solidity of the objects around us and even our own bodies. A physicist stands outside a sealed laboratory while inside, his friend carefully measures a quantum particle. From the friend's perspective, the measurement is complete, the result is clear, and the particle's state is definite. But for the physicist outside, Eugene Wigner, who has not yet looked, a bizarre conclusion is unavoidable. According to the strict rules of quantum mechanics, the entire laboratory, including his friend and all its contents, must remain in a blurred superposition of states until he personally opens the door and asks for the result. This is Wigner's friend, a paradox that pushes the measurement problem to its absolute limit. It forces us to ask whose observation truly counts. Does reality solidify for the first conscious being who looks, or is it dependent on every single observer in a chain? If the friend's consciousness is sufficient to collapse the wave function, then Wigner should find a single, settled reality. But if it is not, then Wigner himself could, in theory, perform a measurement on the entire lab from the outside and interfere with the superposed results, potentially erasing his friend's definite experience. This introduces consciousness itself as a possible player in the physics of reality, suggesting that the classical world of definite facts may not emerge until it enters a conscious mind. The implications are staggering. One interpretation insists that the friend's observation is the real one, and Wigner is simply ignorant of a fact that already exists. Another, more radical view argues that both perspectives are equally valid, and the universe only resolves its contradictions when all observers compare notes, creating a consistent shared reality. This paradox reveals that we lack a clear, objective line where the quantum world ends and the classical world begins. Is it at the size of an atom, a cat, a measuring device, or a human brain? The very definition of an observer becomes hopelessly murky, pointing toward the need for a theory that can seamlessly bridge these realms without relying on such fuzzy boundaries. This struggle to define a single objective reality from multiple perspectives leads us to question the very stage where this drama unfolds, the nature of space itself. Einstein himself grappled with a strange consequence of his own theory of general relativity, a puzzle so deep it threatened the very meaning of location. Imagine you have a complete map of the entire universe, every star, planet, and gravitational field. Now take all the matter and energy in one region of space, a so-called hole, and mathematically shift it, dragging the entire gravitational field to a new set of points in the void. According to the equations, both descriptions, the original and the shifted one, describe the exact same physical reality. No experiment could ever distinguish between them. This is the whole argument. It creates a devastating question. If the points of spacetime have no inherent identity, and we can shuffle events around without changing anything observable, then what are we actually talking about when we say something happened here versus there? The resolution is as profound as the paradox itself. Spacetime points are not individual actors on a stage. They are defined entirely by their relationships to each other, by the gravitational field and the events that occur. The stage itself has no fixed markers, only the dynamic connections between objects and forces. This principle, known as diffeomorphism invariance, tells us that the universe is not a container, but a web of interrelated events. The only things that are physically real are these relationships, not the points themselves. This insight was crucial for the development of general relativity and continues to shape our quest for a theory of quantum gravity. It reveals that the fabric of the cosmos is not a passive backdrop, but an active, dynamic participant in the unfolding of reality. This relational view of space and time, where location is defined by connection, finds a startling echo in the quantum realm, where particles defy any notion of separate existence altogether. The strange, instant connection of entangled particles seems to offer a cosmic shortcut, a way to shout across the galaxy without delay. Yet this tantalizing possibility is an illusion, a cosmic dead end for faster-than-light messaging. The reason lies in a powerful piece of quantum logic known as the no-communication theorem. Imagine you and a friend each hold one of a pair of entangled particles. You agree that if you measure your particle and find it spinning up, it means one thing, and spinning down means another. It feels like a perfect, instantaneous code. But here is the catch: you cannot control what result you will get. Your measurement is completely random. You might get spin up or you might get spin down with a 50-50 chance. The moment you look, your particle randomly picks a state, and your friend's particle instantly mirrors it. But from your friend's perspective, nothing has changed at all. They just see their own particle randomly choosing a state as well. They have no way of knowing whether you have already measured your particle or are still waiting. The correlation between the two results is only revealed later, when you both get on a slow, classical phone call and compare your random lists of numbers. Without that ordinary, light-speed limited conversation, the entanglement is useless for sending a deliberate message like help or hello. The spooky action is real, but it is spooky randomness, not spooky messaging. This theorem resolves the apparent conflict with Einstein's relativity. No information, no signal, and no energy actually travels between the two particles. The universe preserves causality by ensuring that the random outcome on your end cannot be used to impose a specific, meaningful outcome on the other. This very limitation, however, becomes a powerful tool. In quantum cryptography, this shared randomness is the key to ultimate security. Two parties can use entangled particles to generate a secret, random key for encoding messages. Because any eavesdropper trying to listen in would have to measure the particles, their intervention would inevitably disturb the delicate entangled state, introducing errors that the legitimate users can instantly detect. The attempt to spy announces itself, making the communication perfectly secure. The no-communication theorem draws a fundamental boundary for quantum technology, revealing that the universe's deepest connections are not channels we can command, but a shared, random dance that we can only witness after the fact. This understanding of quantum boundaries leads us to a final temporal puzzle where quantum mechanics meets the relentless flow of time. A watched quantum pot never boils. This bizarre statement captures the essence of the quantum Zeno effect, a phenomenon where constant observation can freeze time for an unstable particle. An atom poised to decay, a radioactive nucleus ready to split, can be held in a state of perpetual potential simply by measuring it repeatedly and rapidly. It is named for the ancient Greek philosopher Zeno, who argued that a flying arrow is motionless at any single instant and therefore can never truly move. In the quantum realm, this philosophical puzzle becomes a startling physical reality. The effect arises from the very heart of quantum mechanics, the wave function collapse. When a quantum system is left alone, its wave function evolves smoothly, spreading out like a ripple in a pond, exploring different possibilities, including the possibility of decay. But a measurement is a violent interruption. It forces the system to pick a single state, to collapse its wave of possibilities into one concrete reality. If you measure it immediately after this collapse, it is almost certainly still in its initial state, having had no time to evolve. By measuring it again and again in quick succession, you keep resetting its internal clock. You are essentially asking it, "Are you still here?" over and over, and it never has a chance to answer no. This has been demonstrated not with hypothetical atoms, but in real laboratories. Scientists have used rapid laser pulses to observe particles, and indeed, the more frequently they looked, the more they suppressed the natural evolution and decay. This turns our classical intuition on its head. We assume that looking at something is a passive act, that we are merely gathering information. But in the quantum world, observation is an intervention. It is a physical process that actively shapes the behavior of reality. This profound insight is not just a curiosity, it has powerful implications for the fledgling field of quantum computing. In a quantum computer, the delicate quantum states of qubits are easily disrupted by their environment, a process called decoherence. By strategically applying the quantum Zeno effect, engineers can, in a sense, protect these qubits. They can use frequent, controlled measurements to lock the qubits into their desired states, preventing them from drifting into error. Here, the act of watching becomes a tool for preservation, a way to fight the natural chaos of the quantum world. This paradox reveals a universe where the observer is not a detached spectator, but an integral player whose very gaze can halt the flow of time for a single particle. If our attention can shape the fate of a quantum system, it forces a deeper question about the fate of the entire cosmos and the mysterious force that is pulling it apart. The silent, frozen fate of the heat death seems like the universe's final word. All energy evenly spread, every star long extinguished, and no possibility for change ever again. This is the ultimate victory of the second law of thermodynamics, a state of maximum entropy where the cosmic story simply ends. Yet this chilling conclusion rests on a critical assumption that our universe is a single, isolated system with a finite amount of energy, drifting toward an eternal equilibrium. But what if it is not? If the cosmos is truly infinite or part of a grander cycle, then this final silence might be nothing more than a local event in a much larger, more dynamic meta-reality. In an eternally inflating multiverse, new pocket universes could be continuously bubbling into existence, each with its own laws and its own low-entropy starting point. Our entire cosmic history, from the Big Bang to the last fading ember, would be just one episode in an endless series of creations. The heat death of our particular bubble would not be the end of everything, merely the closing of a single chapter in an infinite book. Another profound idea comes from quantum theory. Even in the absolute cold and stillness of the final heat death, the void would not be truly empty. Quantum fluctuations would still occur, tiny tremors in the fabric of spacetime. Given an almost unimaginable amount of time, one of these random fluctuations could, by pure chance, be large enough to trigger a new Big Bang, birthing a fresh universe from the ashes of the old. This cosmic renewal would not require any outside force, just the endless patience of quantum possibility in an eternity of silence. This paradox forces us to confront the scale of eternity itself. Is our universe on a one-way trip to permanent stillness, or are we merely witnessing a single phase in an eternal dance of death and rebirth? The answer depends on the deepest, still unknown architecture of reality, on whether our cosmos is alone or one member of an infinite ensemble. The contemplation of such ultimate endings and beginnings brings us to a paradox that operates on a much more human scale, challenging how we reason about chance and make decisions under uncertainty. A coin toss dictates the rhythm of Sleeping Beauty's reality. She agrees to a strange experiment where she is put to sleep on Sunday. A fair coin is flipped. If it lands heads, the researchers wake her once on Monday. If it lands tails, they wake her on both Monday and Tuesday. But after each awakening, they give her a drug that erases her memory of the previous day. So every time she is awakened, she has no idea if it is Monday or Tuesday, or how many times she has been woken before. The question is, in that moment of groggy consciousness, what should she believe the probability is that the coin landed on heads? Your immediate intuition might scream 50-50, it is a fair coin after all. Yet a powerful counterargument suggests she should say 1/3. The reasoning is based on the total number of awakenings. There are 3 possible awakening events that feel identical from her perspective: a Monday heads awakening, a Monday tails awakening, and a Tuesday tails awakening. Only one of these 3 events corresponds to the coin showing heads, so if she believes each awakening is equally likely, the probability of heads is only 1 in 3. This is the Sleeping Beauty problem, a deceptively simple puzzle that has split the world's greatest thinkers into 2 fiercely divided camps, the halfers and the thirders. The halfer position clings to the objective fact of the coin toss. No new information about the coin's outcome has been given to her upon waking, so she should not change her initial belief that the chance of heads is 1/2. The thirder position, however, argues that the context of the awakenings itself is the new information. She knows she is in an awakening, and awakenings happen more often when the coin is tails, so she should update her belief accordingly. This debate cuts to the core of what probability even means. Is it a measure of the state of the world, a fair coin in a box, or is it a measure of our own personal ignorance and self-location within a set of identical experiences? This paradox forces us to ask, what does it mean to be me at this moment with this specific set of memories? The implications ripple out from this enchanted castle into the vastness of cosmology. When we ask why the universe seems so finely tuned for life, we are in a position eerily similar to Sleeping Beauty. We find ourselves existing in a universe that permits our existence. But how many other lifeless universes are out there? If our cosmos is just one awakening in a multiverse of mostly dead worlds, then our surprise at the perfect constants of nature might be a form of cosmic survivor bias. The probability that we would observe a life-friendly universe might be quite high, not because such universes are common, but because we can only awaken in the ones that allow for consciousness. The Sleeping Beauty problem shows that probability is not a fixed number on a page, but a fluid concept that shifts with our perspective and the very context of our existence. It challenges the bedrock of our intuition, revealing that chance itself might be a story we tell ourselves about our place in a much larger and much weirder ensemble of possibilities. This profound questioning of evidence and perspective leads directly to a final paradox, one that pits the random heart of quantum mechanics against the unyielding chain of cause and effect. John Bell tore a hole in our comfortable classical worldview with a theorem of devastating clarity. He provided a mathematical test to settle the debate Einstein had started with his spooky action. The theorem proves that no theory relying on local hidden variables can ever reproduce all the strange predictions of quantum mechanics. Local realism is the intuitive idea that objects are only influenced by their immediate surroundings, and that they possess definite properties whether we measure them or not. It is the bedrock of how we experience the world. Bell showed that if local realism is true, then the correlations between entangled particles must obey a certain limit, a rule now called Bell's inequality. But quantum mechanics boldly predicts that entangled particles will violate this inequality, displaying a stronger connection than any local, real universe should allow. For decades, this was a philosophical argument. Then technology caught up and scientists performed the experiments. The result was unambiguous. The particles violated Bell's inequality every time. The universe had voted, and it voted for spookiness. This forces a brutal choice. We must abandon either locality, the principle that distant events cannot influence each other faster than light, or realism, the principle that objects have definite properties independent of measurement. We cannot keep both. Most physicists choose to sacrifice local realism. This means accepting that the universe is fundamentally non-local, that entangled particles share a connection transcending space, or that properties like a particle's spin do not actually exist until the moment they are measured. There is no hidden clockwork, no deeper, deterministic reality hiding beneath the quantum weirdness. This paradox is not a minor curiosity. It is a cornerstone of modern physics. Its resolution supports breathtaking interpretations of reality, from the many worlds view where every possibility blossoms into a new universe, to Bohmian mechanics, which preserves realism but at the cost of embracing an explicit, instantaneous interconnectedness across the cosmos. Bell's theorem dismantled our classical intuition and revealed a universe far more mysterious and interconnected than we ever dreamed. This profound shift in understanding reality from the quantum scale forces us to confront how information itself behaves in the most extreme environments imaginable, within the gravitational abyss of a black hole. A black hole's evaporation creates a startling timeline for the escape of its deepest secrets. As it steadily shrinks through the emission of Hawking radiation, the scrambled information about everything it ever consumed must eventually reemerge. But when does this cosmic data release actually begin? Physicist Don Page performed a meticulous calculation, and his answer was both precise and deeply puzzling. He determined that the information starts to leak out only after the black hole has passed the halfway point of its incredibly long life, after it has already lost half of its original mass. Until that moment, the radiation appears to be purely random, carrying no discernible fingerprint of the fallen matter. But after this Page time, the radiation becomes subtly correlated, imprinted with the hidden history of the black hole's past. This creates a severe conflict with one of the most sacred principles in physics, unitarity. In quantum mechanics, unitarity demands that information is never truly lost. It must be preserved and in principle recoverable throughout any process. If the information only begins to escape halfway through the evaporation, what happens during the first half of the black hole's life? From a quantum perspective, it would seem that information is effectively lost for a vast stretch of time, only to miraculously reappear later, violating the smooth, continuous evolution that unitarity requires. It is as if a book was completely burned to ash, but then halfway through the fire, the ashes spontaneously began to reassemble themselves into legible pages. The paradox forces us to confront a bizarre possibility, that a black hole must somehow remember everything it has swallowed, keeping that information perfectly hidden until a specific trigger moment in its old age. Resolving this demands a radical rethinking of the black hole's interior. Perhaps the information never actually falls into a central singularity. The holographic principle suggests it is always stored on the surface of the event horizon, like a vast cosmic hard drive. From this perspective, Hawking radiation is not born from the void, but is a direct result of subtle interactions at this energetic boundary. The radiation slowly reads the data encoded there, but only after the black hole has shrunk enough does the information become legible in the outgoing energy. This paradox reveals that black holes are not the simple, silent graves of general relativity, but incredibly complex quantum systems with a rich and dynamic life cycle. They are not static pits but evolving entities with an internal structure and a memory that unfolds in stages. The struggle to pinpoint the exact moment information breaks free shows us that even nothingness, the quantum vacuum from which Hawking radiation springs, holds a deeper story. The most fundamental question is not how the universe began, but why it exists at all. Why is there a magnificent, sprawling cosmos instead of a silent, eternal nothing? This is the ultimate paradox of existence, a puzzle that physics and philosophy struggle to answer in equal measure. The sheer presence of something, of anything, seems to defy logic. We are accustomed to events having causes, but if the universe is the totality of everything, what could possibly have caused it? The very framework of cause and effect may break down at this absolute beginning. One compelling scientific idea is that our vast universe emerged from a quantum fluctuation in a perfect void. In this view, the total energy of the cosmos is precisely zero. All the positive energy bound in stars, planets, and galaxies is perfectly balanced by the negative gravitational energy pulling everything together. The universe could be the ultimate free lunch, a grand eruption from nothing that required no input of energy because its net value remains, and always has remained, zero. Another proposal is that true nothingness is inherently unstable. A state of absolute non-existence might be as improbable as a pencil balanced perfectly on its tip, inevitably tipping into the reality of something. The quantum foam that characterizes empty space suggests that void is not peaceful, but a seething cauldron of potential, constantly birthing and annihilating virtual particles. Perhaps a universe is just the one fluctuation that succeeded, inflating beyond the point of no return. Yet other thinkers argue the question itself is malformed, a trick of language. The concept of nothing may be a human invention with no true counterpart in reality. We ask why there is something rather than nothing, but the question presupposes that nothing is a default state, a plausible alternative to being. What if being is the only possibility? What if the universe, in some form, is a necessary, logical consequence of mathematical truth with no need for an external cause? This paradox forces us to confront the hard limits of explanation. Science describes how the universe evolved from a hot, dense state, but it hits a wall of mystery at the moment of creation itself. We are left gazing into an abyss where our most reliable tools fail. The awe we feel when looking at the stars is not just about their beauty, but about the profound, unsettling miracle that they are there to be seen at all. This deep wonder at existence itself leads us to the final frontier, where the rules of the very small meet the laws of the very large. Our most successful theories of reality cannot agree on what time actually is. Einstein's general relativity paints time as a dynamic and malleable fabric, woven together with space, stretching and compressing in the presence of mass and energy. Your clock ticks at a different rate than a clock on a satellite, proving time is relative. Yet in the quantum realm, the rules that govern atoms and particles treat time as a fixed and universal background, an unchanging stage upon which the quantum drama unfolds. This glaring contradiction is known as the problem of time, and it is the single greatest obstacle to uniting these two pillars of physics into a single theory of quantum gravity. If we cannot reconcile what time is, we cannot understand the universe's first moments, when the cosmos was so small that both general relativity and quantum mechanics must have been in play. Some approaches, like loop quantum gravity, propose a radical solution that time is not fundamental at all. In this view, time emerges from the relationships between more basic building blocks, perhaps a network of discrete spacetime loops. The flow of time we experience would be a collective illusion, a consequence of how these fundamental elements interact, much like the temperature of a gas emerges from the frantic motion of countless molecules. An even more startling idea comes from the Wheeler-DeWitt equation, a cornerstone of quantum cosmology. This equation describes the entire universe as a static, frozen block. It has no time variable at all, presenting a reality where the past, present, and future all exist simultaneously in a single, timeless state. This directly attacks our most intimate experience, the feeling of time as a flowing river, carrying us from one moment to the next. If time is not fundamental, what creates the arrow of time we perceive? Why do we remember the past and not the future? The answer may lie in that initial low-entropy state of the Big Bang, creating a powerful gradient that gives the illusion of a direction, even in a fundamentally timeless reality. Our conscious awareness of change, the very sense of a present moment, might be a story our brain tells itself as it processes information in this unfolding cosmic structure. Resolving this paradox is not just an academic exercise. It is the key to unlocking the final secrets of the cosmos, forcing us to ask if our own conscious observation plays a role in weaving the tapestry of time itself. The soft glow of a sunset, the sharp sting of a cut, the rich taste of chocolate, these are not just data points. They are experiences, the private, inner movie of consciousness that each of us lives. And this simple fact of feeling presents perhaps the most intimate paradox of all, the hard problem of consciousness. While science can map the brain's circuitry, explaining which neurons fire when we see the color red, it hits a wall when asked why those electrical signals should be accompanied by the actual, raw sensation of redness itself. This is the profound puzzle articulated by philosopher David Chalmers. How does the objective, physical stuff of the brain, a 3-pound lump of gelatinous matter, generate the subjective inner world of thought, emotion, and qualia, the what it is like to be you. This is not just a question for biology, it reverberates through physics and cosmology. Some interpretations of quantum mechanics, troubled by the measurement problem, have even speculated that consciousness itself plays a role in collapsing the wave function, that observation requires a mind. While this remains a highly controversial fringe idea, it highlights the deep unease about where the observer fits into our picture of reality. A more expansive and equally startling proposal is panpsychism. This view suggests that consciousness is not a late-arriving product of complex computation, but a fundamental property of the universe, as basic as mass or charge. In this picture, even an electron might possess a tiny spark of proto-consciousness, a dim experience of the world. When these simple elements combine in the exquisitely complex structure of a brain, they give rise to the rich, unified consciousness we enjoy. This directly challenges a purely materialist explanation of the universe, forcing us to consider that the interior world of mind might be as real as the exterior world of matter. The implications are staggering. If consciousness is fundamental, then our entire cosmological story is missing a vital ingredient. It also forces a rethink of artificial intelligence. Could a sufficiently complex computer ever truly feel anything, or would it merely be a sophisticated simulation of feeling, a hollow shell going through the motions without an inner light? Solving the hard problem requires bridging an apparently unbridgeable gap, the chasm between the third-person description of objective science and the first-person reality of subjective experience. It asks if a complete theory of everything must ultimately include an explanation for why there is something it feels like to be part of that everything. This profound mystery of inner experience stands in stark contrast to a puzzle about the universe's grandest, most impersonal scale. The cosmos appears suspiciously smooth. Look in any direction and you find a universe of startling uniformity, with the distant reaches of space sharing the exact same temperature and density. This cosmic sameness presents a profound puzzle known as the horizon problem. For two regions to achieve the same temperature, they must have once been in thermal contact, able to exchange energy and balance themselves out, much like ice cubes melting in a glass of water to create a uniform temperature. But when we trace the history of the universe back to its earliest moments, a conflict emerges. The cosmic microwave background radiation, the leftover heat from the Big Bang, shows this perfect uniformity across the entire sky. Yet, given the finite age of the universe and the ultimate speed limit of light, there simply hasn't been enough time for heat to travel between these vastly separated regions. They exist beyond each other's cosmic horizons, forever out of touch. It is as if people on opposite sides of the world who have never communicated were all singing the same song in perfect unison. How could this coordinated cosmic symphony have been arranged? The leading solution is a breathtaking event called cosmic inflation. This theory proposes that a tiny fraction of a second after the beginning, the universe underwent a growth spurt of almost unimaginable ferocity. Space itself expanded faster than the speed of light, stretching a subatomic speck of primordial cosmos into a volume far larger than our entire observable universe today. This violent, exponential smoothing ironed out any primordial wrinkles and unevenness, setting the same temperature everywhere before this inflationary epoch ended, and the more sedate expansion we see today began. The theory is powerfully supported by the precise patterns of slight temperature variations imprinted on the cosmic microwave background, a faint echo of those quantum fluctuations stretched to cosmic proportions. This paradox and its resolution force us to confront the very initial conditions of our universe. The Big Bang model does not explain why the cosmos started in such a smooth, orderly state. Inflation provides the mechanism, a dynamic process that actively created the homogeneity we now observe. It explains the large-scale structure of the cosmos, showing how the seeds of galaxies were sown by microscopic quantum jitters magnified to astronomical scales. The universe became uniform not by chance, but through a dramatic, transformative event that set the stage for everything to come. This grand solution to a cosmic-scale paradox brings our journey to its final steps, where we must confront one last, deeply unsettling implication of the quantum world. A gun is pointed at your head, its trigger linked to the spin of a single quantum particle. You pull the trigger. In one reality, the particle's random outcome spells your immediate end. But in another, you hear nothing but a harmless click. According to the many worlds interpretation, both of these outcomes are equally real. The universe splits, and both versions of you continue forward. Now imagine repeating this experiment. Again and again, you pull the trigger. In countless branching realities, you die. But from your own singular perspective, you will only ever experience the sequence of events where the gun fails to fire every single time. You become a quantum immortal, forever surviving against impossible odds. This is the quantum suicide paradox, a thought experiment that pushes the logic of many worlds to its most unsettling extreme. It suggests that from a first-person viewpoint, you are fated to always find yourself in a universe where you continue to exist, no matter how low the survival probability may be. This forces a brutal question about identity. Are you the same person across all these branches? The you that dies is just as real as the you that lives, but your stream of consciousness only follows the path where survival is possible. It feels like luck, but it is a mathematical certainty within the branching multiverse. This paradox also twists our understanding of probability. The chance of surviving 100 rounds of quantum Russian roulette might be astronomically small, but for the conscious observer who lives through it, that probability feels like 100%. Their personal reality is a relentless series of lucky breaks, a timeline curated by the simple fact that they are there to witness it. Of course, this is a pure thought experiment, a logical ghost we can contemplate but never truly test. Yet it serves as a powerful finale, illustrating just how profoundly the many worlds interpretation reshapes concepts of life, death, and the self. It suggests that in the grand tapestry of the multiverse, your conscious experience is not a single thread, but one strand in an infinite weave of possibilities, always finding a way to continue. These 40 explanations for the universe's most puzzling paradoxes have taken us from the blurry edges of quantum particles to the vast, silent horizons of cosmology. We have seen how light can be both a wave and a particle, how time stretches and warps for different observers, and how black holes might encode our reality like a cosmic hologram. We have grappled with the illusion of free will, the fine-tuning of the cosmos, and the possibility that everything we know is a simulation. Each paradox is a crack in the surface of our understanding, a glimpse into a deeper, stranger reality. They reveal a universe that is not a collection of separate objects, but a deeply interconnected and often baffling whole. The journey does not end here, it merely opens a door. The greatest paradox of all may be that the more we learn, the more we realize how much remains wonderfully, mysteriously unknown. Our journey through 40 cosmic puzzles reshapes the very ground beneath our feet. We have stood beside Schrödinger's cat in its box of blurred reality, and we have listened with Fermi to the profound silence of a seemingly empty cosmos. Each paradox, from the spooky entanglement of particles to the holographic encoding of our universe, is more than a riddle. It is a fracture in the mirror of our understanding, revealing a deeper and stranger truth behind the reflection. These are not mere intellectual games, but the very frontiers where human knowledge meets the unknown, a landscape where every mystery solved unveils two more waiting in the shadows. As you reflect on these ideas, let them alter your perception. The solid chair you sit on is a whirl of quantum probability, the arrow of time a consequence of a cosmic beginning, and the night sky's darkness a testament to an expanding universe with a finite past. This pursuit is the engine of our progress, driving technologies like quantum computing and pushing the very limits of philosophy. Thank you for embarking on this exploration of reality's greatest enigmas. If these glimpses into the cosmos resonated with you, please like, subscribe, and share your own thoughts and questions in the comments below. Keep questioning, keep exploring, and until our paths cross again, stay endlessly curious about the universe's beautiful, endless mysteries.